Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. We've derived the attenuation bias formula and worked through numerical examples, so now let's see it in R. First with real data, then with synthetic data, where we know the exact truth and then can verify the formula precisely. So without further ado, let's switch to R. For this particular video, we'll be using again the Wooldridge library and we'll be using ggplot2 so that we can visually see the differences in the betas. And we're going to use the library Wage2, which we have also seen in previous videos. We're going to first run the OLS with true education as the best baseline, and then we'll see how the results change when we simulate measurement error in education. So let's load the data first and then run and save the regression for the true data. So we can see here education is statistically significant and the actual beta is 0.07. We're going to just make sure we save that. And as you can see, it's right away given for us again. Now, for simulating the measurement error, we're going to use the seed and we're going to do this with three different scenarios. So we're going to add classical measurement error when we're going to add small noise, so the error variance is 25% of the true variance. Then we're going to do medium noise, where the error variance is 100% of the true variance, and ultimately large noise, where the error variance is 300% of the true variance. Now, keep in mind, in real life, we can't really do this because we never observe the true X, but in a simulation we can, and it's exactly why simulation is so powerful for understanding bias. So let's run the code for the simulation first, and keep in mind we're going to run the regressions all over again for all of these three cases, and the actual regression, so education, experience, and tenure, they are still the same everywhere, apart from now, instead of like the original education, we're gonna have education noisy small, noisy medium, noisy large, while experience and tenure still remain the same. So let's run the three regressions and save the beta coefficients for each of those cases. We'll see the comparison for all of those, so just be a little bit patient and you'll see. Before we see them, there's one last bit that we will do in terms of computation. If you remember, we have the theoretical attenuation bias, like the factor from our formula, which is the lambda sigma square x star divided by the sigma square x star plus the sigma square v, because we also had like the noise. Now, we're going to compare the formula's prediction to what OLS actually gives us, okay? And this is exactly what like step 5 is doing. So first we're computing the theoretical attenuation factors based on the fact that we have both regressions in here. So the lambda for all the cases is the variance of your x star, like what we believe is the true observation, and then x star plus the v small in here, like the variance. And the predictions. Now, keep in mind, for the predictions for the small, medium, and the large, we'd have to take the true beta and then multiply it for the respective lambdas when we have small, medium, and large noise. Let's put everything in a summary table to see how they all compare to each other. So we've got in the scenario, right, where we have no measurement error. Theoretically, the lambda should be exactly 1. We have that the beta was 0.049, okay, and the prediction and the actual in this case are exactly the same because, as again, in the first case scenario, we were using the true one. Okay, so for the true one, it predicts exactly the OLS what the OLS produces, okay? Now, for the small, for instance, we have a calculation of the lambda factor of 0.8, which means if we had multiplied the 0.8 to the 0.07, we should have gotten the 0.059. So that would have been the prediction. What we actually get is 0.0561, which, as you can see, is very similar. And the true variance of the X was only like 74.9. So it's like almost 75% because we said that the noise was 25%. Okay. Now, what happens when we move from small, medium to large noise? As you can see, the lambda is becoming smaller and smaller, just like we saw in the previous video. We have the beta becoming smaller and smaller. So going from the true 0.07 to 0.059 to 0.0374 and then 0.018. So as you can see, it's going down to zero. Okay. Now, what's happening in here is that basically the theory and the simulation are agreeing. We can also see this visually, so we can plot all of the cases just to see like how they compare with the actual true where we were expecting it. So in here, the dashed line in here is where the true beta was, the 0.075. As you can see, the more noise that it's added, the estimation starts to go down until we have this like very small beta in here, okay? Because we had 300%. So each bar is what the OLS estimates with increasing measurement error would be. And they are falling further below the truth as noise is increasing. And this is literally attenuation bias made visible. For the second bit of the video, we're going to see the synthetic variation. Now, why synthetic data? With real data, as we said, we never truly know the correct answer, so we're comparing OLS with noisy education, not to OLS with reported education, which may itself have some error. Now, what synthetic data does to solve this is that we generate the data ourselves, so we know the exact truth. Okay, so we know that the beta 1 is 4 exactly, there's no ambiguity in it, and we're just gonna generate the synthetic data. We're gonna have a number of observations of 1000, so, and we're making sure that our beta 1 is 4, like the true effect. And we're adding all of the other elements for the regression. So ultimately, the model that we have is going to be based on all the information that are already given. With the true, okay, with the true X star, which we're going to be using there, the OLS recovers approximately 4. So this is what we should expect to see. And after that, we're going to add measurement error to see what happens after. So let's generate all of the synthetic data first based on this information. So we're controlling here the environment, and then we're gonna run the OLS with the true X star. So as you can see here, we're running OLS synthetic true where we've got the Y on the X star. And before we compare with anything else, so look here, the beta is the 4. Now we're going to add the measurement error to verify the attenuation formula. And we've got here the noise levels, as you can see, 0, 1, 3, 6, 9, 18. For each noise level after that, we're going to run the regression and to record all of the beta hat, so the estimations. And keep in mind, for each level of noise, we're adding a random error to the X star, okay? Running the OLS, recording the coefficient, and ultimately we'll see how they all compare to each other. So let's run first all of the noise. And now let's see if we can check all of the results one after the other with the ggplot. Let's see what the graph will tell us this time. So in this new graph where we've got like the formula versus the simulation attenuation bias, we've got the blue dashed line is what the formula predicts. So as you can see, it's right here. The orange points are what the OLS actually produces. Now, they match almost exactly, and this is the most important result in this video because if you remember, the formula for the beta hat is that it's equal to beta times the lambda, and it shouldn't be an approximation. It is exactly what the OLS does under classical measurement error. So theory and simulation are virtually indistinguishable in this case. Overall, there are three main key takeaways from the video. So as you saw visually, more noise is added, more attenuation, like the bars in the real data chart that we showed earlier clearly indicated that. The formula works, so theoretical predictions match the simulated OLS almost exactly. And as you can see, the bias is systematic, so it always goes towards zero and never away from it. In our simulating measurement error confirms that OLS estimates shrink towards zero in exactly the amount that it's predicted by the formula beta hat being equal to beta times lambda, where the lambda is the sigma square x star divided by the sigma square x star plus the sigma square v. In the next video, we'll implement the IV fix in R using Wedge2 dataset again to show like how a valid instrument recovers the true coefficient that measures that the measurement error was hiding. So stay tuned and I'll see you then.